let's get started. We are going to discuss chapter 1 here, which is about the materials engineering concepts. Okay, so in the first chapter, we are going to have concepts about the materials in civil engineering. We have material that is common in civil engineering. We are going to use it frequently, like the steel. Many of you see buildings made from steel. And also we have the concrete and we have the aggregates. Actually, the aggregate, we are going to use the aggregate in order to make concrete and also in order to make asphalt concrete. Okay, so we are going to use the aggregates in order to make concrete and to make asphalt concrete. I think most of you saw building made from concrete. Actually, here in this city, most of the building here made from concrete. And also we have the masonry, the bricks, and also we have the wood, and we have the soil. And regarding the soil, we are not going to discuss the soil here in this course because we don't have room for the soil here, because the soil, it has a lot of information about it, and it's very important civil engineering material. So it has a course called soil mechanics. So you are going to get the soil mechanic course, and in that course you are going to study everything about the soil. But here in this course we don't have room for the soil. We have lesser material. We are not going to use that material a lot, not like those material here, like the aluminum. We are not going to use the aluminum a lot in civil engineering. Actually, the aluminum, it could be used to manufacture cars and airplanes, but we are not going to see the aluminum a lot. Maybe if you are going to manufacture a door, window, something like that. That is why it's the less common materials. Also the glass and the plastic and the fiber reinforced composite. So like you can see here, I have a number of materials, but which one should I select in order to construct my structure? In order to answer this question, I have criteria in order to choose the suitable material. The first criterion for that is the economic factors, which mean that how much the material is going to cost. What about the transportation? How I'm going to transport the material from the source to the job site? How to place the material itself? The manufacturing cost. So I need to know the economic factors. Also, I need to know the mechanical properties. I need to know how much the material is going to sustain a load. I need to know about the deformation of the material if I'm going to apply a load for that material. So mechanical properties, it's mean that how the material is going to respond when I'm going to apply a load. Okay, you need to know whether the material is strong or weak. Also, I have the non-mechanical properties, like the density of the material. You have material with high density, or we are going to have material with low density. So I need to put that in my mind. Okay, like also how the material is going to respond to thermal properties. And also I have the production and the construction, how I'm going to construct the building itself, how I'm going to produce the material. It's very important criteria. And also I have the aesthetic properties, like the appearance of the material, whether it's beautiful material or ugly material. And also I have the sustainable consideration, whether the material is going to be friend with the environment or not. So in order to choose the material, I have a criteria in order to choose the suitable material. And we will not forget the client's need. For example, maybe the client need a beautiful material, or also we should not forget about the facilities function. For example, if you are going to construct a mall, you know that in the mall we need to have large spans. So in that case, maybe the steel is the most suitable choice. So I need to put emphasis on the client's need and the facilities function. It's very important factors in order to help me to select the material. So again, I have many materials, like you can see here. In order to select the suitable material, I need to look over all of these criteria. When we say that economic factors here, it's not mean just the cost of the material. It also means the availability and the cost of raw materials. For example, here in this city, you don't see a lot of houses that made from wood, because we don't have a lot of woods here. So the availability factor here is going to affect that. Okay. Also, the manufacturing costs. Here, maybe you are not going to see workers or laborers, those who have experience with the wood, for example. And also the transportation. So sometimes I'm going to use a certain material, but that material needs to be exported from China or from United States of America. So that is going to delay my work. Maybe that material is going to arrive within 1 year or 9 months. So the transportation factor is very important. And also the placing of the material, how I'm going to use that material from the source to the site, how I'm going to put it inside my location. Because sometimes I have difficult locations. Not all the material is going to be suitable to be used in that location. And also the maintenance. I'm not going to choose a material that need a lot of maintenance, maybe every year and something like that. So all of this is going to be considered as economic factors, not only the cost of the material. So we are going to talk about the criteria on how to choose a suitable material. So economic factor discussed it here is not just the cost of the material. We have many factors to be considered. And the mechanical properties. We say that the mechanical properties is the response of the material to external load. So like you can see here, I have cantilever. It's made from the steel. It could be also made from the wood, or it could be made from the concrete. So I'm going to apply a load, and I'm going to see the response of that material. So the mechanical properties, it means that the response of the material to external loads. We know that all the material is going to deform under load. So if I'm going to apply a load, deformation is going to take place inside my material. But that is going to depend on the material properties. For example, if I apply that load, of course you are going to see deflection here. So the deflection is going to be different if the material is steel or it's wood or it's concrete. And also the magnitude at the type of the load. So if I apply, for example, 200 newtons, is going to be different than 1,200 newtons. So that is going to affect the response of the material. And also the geometry of the material element. For example, here I have cantilever. If I'm going to have simply supported beam, the deformation and the response of the material is going to be different. So the response of the material depends on 3 factors: the material properties, whether that material is steel or concrete or wood, the magnitude and the type of the load. For example, here I have concentrated load. It could be a normally distributed load. Then the response is going to change accordingly. And also the geometry of the material element. Here I have cantilever. It could be simple supported beam, and the behavior is going to be different. In order to know that, for example, draw the shear and the bending diagram for cantilever, and draw the shear and the bending diagram for the simply supported beam. You are going to see different shear and moment diagram. And also, it's very important to understand the loading conditions. We have two basic types of loading. We have the static or the dead loads, and we have the dynamic or the live loads. So the static is going to be applied for a long term, and in order to consider a load as static load, it should be applied and removed slowly. So no shocks or vibration. So any load that you are going to put on your structure, that is going to be slowly. You are not going to make shock or vibration. In that case, that load is going to be considered as static loads. Okay? Usually it's going to be due to gravity. While the dynamic loads is going to be applied for a short term. So it's not going to be applied for a long term like the static loads. It's going to be only for short term. We have three types of dynamic load. We have periodic, we have transient, and we have the random dynamic load. The periodic, like repeating wave from rotating equipment. So let's see that you have generator inside your building. So in order to generate electricity, the machine is going to rotate. That rotation is going to cause dynamic loads, and it's going to be periodic, which means that it's going to repeat itself again and again and again. The transient load, let's see that you are going to construct a bridge, and in that bridge, the car is going to go through that bridge. So when the car is going to go through the bridge, that will cause dynamic load. But that load is going to cause quick impulse, and when the car is going to cross the bridge, that impulse is going to stop, or is going to decay back to resting. So you are going to have dynamic load, but after a short time is going to stop. And the last type is the random dynamic load. That type of the load is not going to repeat itself, like the earthquake is going to hit a certain town only once. That type of dynamic is not going to repeat itself. Okay, so we have periodic, like rotating machines, is going to repeat itself again and again and again. And I have the transient, is going to cause quick impulse, and then is going to decay back to resting. And we have the random, which is not going to repeat itself. Also, it's very important to understand the stress-strain relations. Like we say that all solid materials deform under load. So here, if I have a specimen like this one here, and I'm going to apply a force F, and if that length, the original length or the initial length is L, when I'm going to apply a load, that length is going to increase. As a result, I'm going to have delta L. So as a result of that force, I'm going to have deformation. Okay, so all solid materials deform under load. All the materials that we have discussed, the steel, the concrete, when I apply a load, deformation is going to take place. And in order to deal with the materials, for example, if I apply here 100 kilonewton, and here I apply also 100 kilonewton, the response here and here is going to be different. For this case here, with a smaller dimension, 100 kilonewton is going to cause more deformation than that case here. Okay, so I cannot express the response of the material by the force only. I need to put another criteria. For example, I need to include the dimension. Okay, so in order to do that, they introduce the stress. So stress is like force. With the size factor out, we divide the force over the area so that we can directly compare the different sizes. So, for example, the stress for that specimen here, for example, the stress that is going to make the material fail is going to be the same as that one, but the force is going to be different. In this case here, I need more force. In this case here, I need less force. But the stress, if I'm going to have the same material, the maximum stress is going to be the same. That is why we introduce the concept of the stress. So stress equal the force over the area. It could be measured with the PSI, KSI, KPA, megapascal, and gigapascal. Similarly, when I'm going to apply a force, I'm going to have deformation, right? Delta L. So when I'm going to have deformation, of course, if the length here is more than the length there, the deformation here is going to be more than that one here. So I cannot define the material by the deformation. So I need to introduce another term which is the strain. The strain is like deformation, but the size factor out by dividing by the original length. So here the deformation delta L, I'm going to divide it by the original length. And in that case, the strain is going to be the same for this case and for that case. So in order to compare different materials, I need to determine the stress and the strain, because the force and the deformation are not going to help me to compare different materials. And also, very important point, we need to talk about it, which is the stress-strain diagram. In order to know the behavior of the material, it's very important to draw the stress and the strain diagram. So what does it mean by the stress-strain diagram? Here I have a sample, like you can see, and I'm going to apply a force to know how much that sample is going to withstand. I have length L here. I'm going to apply force starting from 0. So the force is going to increase from 0 until failure. So the force is going to be 0, 1, 2, 3, 4 until I get to the maximum force that is going to break the specimen here. So in y-axis, I'm going to record the force, and in x-axis, I'm going to record the deformation. When I apply a force here, let's say that force is 10 kilonewton, then I'm going to have deformation, right? So let's say here I have 10 kilonewton, here I have 1 millimeter. When I increase the force again, let's say the force here is 20 kilonewtons, then the deformation is going to increase accordingly, and so on and so forth, until I reach to the failure. Let's say at that point here, the material is going to break. But like I say, the force and the deformation is not going to give me an idea about the material. I'm not going to be able to compare it with other material. So I need to determine the stress. So in order to convert the force into stress, I need to divide by the area. And in order to determine the stress, the strain, I need to divide by the original length. So in the y-axis, I'm going to have the stress, and in x-axis, I'm going to have the strain. So in y-axis, the stress equal F over A, and the x-axis, the strain is going to equal the deformation delta L over L. So now I can compare the property of that material with any other material. We call this diagram stress strain diagram. So every material, it has a stress strain diagram. For example, here we have the stress strain diagram for the glass and for the chalk, you know, the glass and the chalk. So when I increase the stress, I'm going to have strain. And when you reach the maximum stress, the failure is going to take place here. While the steel, I'm going to have a linear relationship between the stress and the strain, but at a certain point, the curve is going to be like that. Because when the failure is going to take place in the steel, you are going to see a large deformation before failure, not like the glass. When you apply the load for the glass and the chalk, the failure here is going to be take place suddenly, without give you any sign, not like the steel. In the steel, you are going to have large deformation before the failure. For the aluminum, you are going to see linear relation between stress and strain at that point, and then you are going to see deformation. The curve is going to be like that. And here is the stress strain for the concrete, and here is the stress strain for the soft rubber. If you have a rubber, if you apply stress strain, you are going to see a reverse curve. It's obvious here I'm going to have large deformation compared with the stress. So the stress strain diagram is very important in order to compare different materials. And like I said here, every material, it has its own stress strain diagram. And the stress strain diagram is going to help us to understand the behavior of the material. So I'm going to stop here at that point. I'm going to give you a room to ask. But next time we are going to continue our discussion. We are going to discuss the elastic behavior, and we are going to know the difference between linearity and elasticity.